Very good evening to all of you. So we will start this session after 4 to 5 minutes. So please wait. Good evening, everyone. And thank you all for joining us today. I sincerely appreciate your participation in this sixth session of our faculty interaction webinar series on the Atomistic insights into the transition of Armchair Graphene Nanoribbon for the gas sensing application using the Synopsys QuantumATK software. So it is my pleasure to introduce our esteemed speaker for the today's session, Dr. Manoj Kumar Majumdar. So Dr. Majumdar is currently an associate professor in the microelectronics and the VLSI group, electronics and communication engineering at Triple IT near Raipur. He has made yes. So he has made a remarkable contribution to the areas such as nanomaterial and their applications, carbon nanotube and the graphene, nanoribbon based devices, gas sensor, modeling of VLSI device and circuit performance parameters, and emerging electronics. So his research is deeply rooted in the advanced computational methods, pushing the boundary of material science and device application. So, with a strong foundation in the theoretical and the computational physics, Dr. Majumdar has extensively explored the electrical, electronics, magnetic, and transport property of carbon nanotubes and the graphene nanoribbon devices. His work also encompasses modeling and simulation of nanoscale device. So, in today's session, Dr. Majumdar will share his research insight on the leveraging Synopsys QuantumATK software to investigate the gas sensing capability of the Armchair graphene nanoribbons. So his presentation will emphasize how atomic scale modeling and simulation can propel innovation in this field. So following the talk, we will have a live demonstration by the Mr. Kamal Solanki, PhD scholar under the supervision of Dr. Mazumdar. So he will provide a hands-on walkthrough of the Synopsys QuantumATK software, showcasing its practical application in the studying gas sensing mechanism of Armchair Graphene Nanoribbons. So with this brief introduction, I am delighted to hand over the session to our esteemed speaker, Dr. Manoj Kumar Mazumdar. Over to you, sir.
Yeah, thank you, thank you. Thank you, Mr. Deepak, for the brief introduction, and I'm very much thankful to the integrated microsystem team for providing me this opportunity to interact with all the participants. So now I am sharing my slides. Okay, is my slide visible? Is it visible to all of you? Hello?
Yes, sir.
Okay, thank you.
Yes, sir, we can see it. Yeah.
Okay, thank you. So, okay. So, as introduced by Mr. Deepak, so today actually I am going to discuss about the atomistic insights into the transition of Armchair Graphene Nanoribbons for gas sensing applications using the Synopsys QuantumATK software. Okay? And I am currently working at Interplanetary near Raipur in the Microelectronics VLSI group under the Department of Electronics and Communication Engineering. So this is the outline of my talk, wherever I am going to discuss about the brief introduction about the QuantumATK software, followed by the nanoscale device modeling, some of the key materials modeling areas that can be addressed by the QuantumATK, a brief overview along with their transition mechanism, that is some of our initial results that can be described by using the monolayer versus bilayer stability, the dopant placement effects, the width-dependent electronic shifts, and the random dopant-induced conductance transitions. And also we are having the insights gained into the transition behavior. So with this, I would like to conclude, and the references followed by the references of my talk. So this slide is that the what is the QuantumATK and what kind of the comprehensive platform it is generally providing. So as you all know, this is actually a atomistic toolkit based software. So for actually wherever we are basically using it for the nanoscale simulations, and during the simulation engines we may have the different type of the calculators over there. So we can see here we have the facility of the DFT-based plane wave based calculator, DFT LCO calculator, semi-empirical calculator, and the force field calculator. And also we can go, if we can go to the device level, we can also use the non-equilibrium green function, that is the NEGF based function. So basically the first four, that is we can see here the DFT plane wave, DFT LCO or semi-empirical or force field. These four are basically the atomic based software, atomic based calculator, wherever basically the application of this calculation depends on the number of atoms. So if we can have the DFT plane wave calculator, we can have the atomic atoms of the around 10 to the power 3. But whenever we are moving towards the LCO, which one is the most popular calculator over there, we can have the atoms with the 10 to the power 4. For semi-empirical, it is going to be the 10 to the power 5 and force field up to 10 to the power 7. So this way we can increase the number of atoms by using the different calculation platforms. And this is and if we are using the graphical user interface in the Nano Lab, we can have these facilities over there, that is atomic 3D builder, databases, setup calculations, job manager. We can view our results, advanced analysis, Python scripts also we can have, and the NanoLab links. So these are all the facilities has been provided by the QuantumATK tool. And this is the DFT plus non-equilibrium Gibbs function method. So where actually we can simulate the different slab models. So first we can see, okay, this is the first is the slab model. So basically this model is mainly used to observe the surface phenomenon over there. The second one we can see, that is the NEGF based model. So it is basically used to observe the transport and the IV calculations. And third one is the like just the advanced function of the NEGF, that is the surface NEGF, wherever we can observe the transport and IP characteristics with the flow of current in the surface. So this way, basically, we can use the different functional methods using the quantum wise. And here, basically, we can have the accurate tool to study the interfaces and electronic devices. We can have the no finite size and the surface termination effects, no need for the mini layers, that is the slab that we are using over there, and the bias and get to simulate the resistance, capacitance, and the IP characteristics. And the main thing is that it is available with the DFT and the semi-empirical methods. So this is the one of the example from the quantumized tool, wherever we can have the 10,000 atoms that has been simulated using the DFT-based model. And these are the different type of the like the key materials that can be addressed by the quantum ATK. So the first one, we can address the spintronics or the novel memory based devices. Second one, wherever we can address the 2D material based FET devices. Third one is the transistor channel engineering. Fourth one is the surface processes. Fifth one is the metal semiconductor contacts, and the sixth one is the logic and memory interconnects. So this kind of the wide facilities are being available using the quantumized ATK software, wherever we can simulate and we can analyze the atomic level to the device level performance of the materials. So this is the graphical abstract of actually our research. So mainly the graphical abstract is starting with the nanoscience technology. So basically, what is the nanoscience mainly, and or maybe you can say, okay, wherever actually we are going to the deep to deep nano level. So we have the quantum science and the nanoscience. So basically, whenever the domain of quantum science and the domain of nanoscience are getting interface, we can get the quantum nanoscience over there. Okay, so basically, in the case of the quantum science, mainly we can address the superposition in entanglement and the quantum coherence and quantum measurement kind of the theories. Wherever in the nanoscience, we can follow the two type of the approaches. Either one we can get the top-down approach, and another one is the bottom-up approach. So in the case of the top-down approach, basically we can have the quantum dots and the superconducting devices. Top-down approach means that is we should have to come from the bulk material to the atomic level, and bottom-up approach means you should have to go from the atomic level to the epitaxy level. So that is the LPCVD type of the systems wherever we are using, that is the bottom-up approach actually. So this bottom-up approach is mainly focusing on the molecular-based nanoscience, the control defects, and the quantum surface science. So basically, these two domains are mixed up to make the quantum nanoscience, wherever basically these four main verticals can be explored. One is the materials, another one is the tools, devices, and the exploring quantumness. So basically, these four verticals we can explore out of this. So basically, what do you mean by the quantum? So quantum means that is a small. That is whenever the atomic sizes are going to be smaller, that is being referred as a quantum. Okay. So basically, the nanoscale, whenever we are moving towards the nanoscale devices, so there actually we can find out the different kind of the problems. That is where I should make the doping, where the defects are coming. So these are the very critical issues in the nanoscale kind of the devices. So if you can see that in this case of the bulk configuration, we are having some vacancies. Okay, so if these vacancies are being created, so we are not able to place the dopants in the exact vacant places. And whenever with this bulk configuration we are making the devices, the same type of the phenomenon can be happened. These two are the electrodes, and this is the your graphene based material. So using the quantum wise, we can address these defects. So how we can address these defects? Suppose that we can take a graphene sheet. This is actually a graphene sheet wherever the carbon atoms are arranged in the honeycomb lattice structure, and we can see here the dopants are being placed on the particular places. So you can see if there is any vacancies are there, that can be addressed using the quantum based software by placing the dopants at the exact location. So this is the advantage that is for the atomic scale simulation. Whenever we are going to the nanoscale atomic level simulation, we can address those problems using the quantum software, and wherever every atom matters a lot to make it a more accurate material. Now, so there are some of the defects. So we can address some of the defects at the nanoscale technology. So as I already described, the nanoscale devices are mainly operated at the atomic level or the molecular level of the interaction, and they are basically the highly sensitive to the imperfection due to their small sizes. Because whenever the atoms are getting to be the very small sizes, their bond energy are also being going to be very strong. So we have to also take care if there should not be any kind of the defect or any kind of the losses in the case of the atomic level simulation. So these are some of the key impacts of this kind of the nanoscale devices. So if we are making the electrical performance on this case, so here basically the defects such as the missing of atoms or the structural irregularities can lead to the increased electrical resistance affecting the device's overall performance. So this is the one of the problem in the case of the electrical performance, because of the structural irregularities can increase the electrical resistance of the device. And if my electrical resistance of the device can be increased, my device will be getting heat up. Okay, and after a certain point of the time, it may be getting damaged. So we should have to take care this thing. Another one is the device reliability. Okay. So if there is any defect in the atomic scale simulation, then these defects can accelerate the wear and tear. So that can actually make the devices to fail permanently. Then the material properties. In the case of the material properties, the defects can influence the optical properties of the materials, and it will also affecting the interaction with the light. Okay, and this will be the crucial application in the case of the nanophotonics and the optoelectronics. So in the case of the material properties, the defects can also contribute to a huge loss. And last one is the heat dissipation that already I told you. If there is any defect, then there is a efficient dissipation of the heat in the case of the nanoscale devices, and that heat generation can be getting that is to the localized heating, and that can affect the overall device stability and the reliability. Okay, so defects should be addressed in a proper way using the quantum-based ATK software. So and these are the new properties to compare. So using this quantum-based ATK software, so what are the facilities or what are the properties we can address? So we can address the conductance that is called the ballistic transport. So ballistic transport means what? Whenever in the case of the atomic scale simulation, whenever the electrons can flow throughout its mean-free path, that is without any collision, that is called the ballistic transport. So ballistic transport can provide a minimum of the resistance in the case of the quantum material. Another one, we can also analyze the complex band structure over here, and also we can optimize our geometries by using the quantum-based ATK software. Okay. Except of these, we can also address the effective masses, the band gaps of the material, total energies, optical properties, electron densities, charge transfer analysis, density of the states, and the device density of the state. So all these properties we can address using the quantum-wise ATK software whenever we are making some atomic level of the simulations. Okay. And these two tables, that is wherever the table 1 is showing the computational algorithm for the bulk or device configuration. So these are the different parameters that we can use. For the bulk parameters, for the exchange correlation, we can use the GGA, that is called the generalized gradient approximation. For the pseudopotential, we can use the FHI, that is called the Fridge Haber Institute, and the basic set we can use the DZP, that is the double zeta polarized. In the case of the device parameter, using the semi-empirical calculator, we can use the parameterization as a extended Huckel theory, the parameter as a Hoffman, and screen as a unpolarized. And in table 2, we can see the numerical accuracy for the bulk devices. So these are actually the different kind of the properties wherever we can actually make changes whenever we are doing the quantumized simulation, the occupational broadening, K-point sampling, everything we can do. And this thing you can see in the live demonstration by my research scholar just after this presentation. So now actually I will try to just discuss some of my research so that we have been carried out in the last 2 to 3 years using the quantum-wise ATK software. So in the first research, basically I would like to discuss about the insightful overview of the PM 2.5 pollutants that can have the sensing substrates and the physics behind the gas absorption. Okay. So firstly, so before coming to this research, we have to first know what is the PM 2.5 mainly. Okay, so PM 2.5, this is a very common name. I think that all of you know everywhere, wherever the environmental pollution and all these things are being attached to our society, we are generally using this term PM 2.5. PM 2.5 means that is called the particulate matter that has the 2.5 micrometer or lesser or less than of that the particulate matter size. So we can see here the particulate matter size below 2.5 micrometer is really harmful for our body, but it is depends on the density of this contaminants in the air. So basically we can see this table. If you can refer to table 3, you can see if the PM 2.5 density is around the 0 to 12, it is not so much harmful, so it is good. If the air quality index is 0 to 50, it is okay or it is good. If the PM 2.5 contaminant is increased from 12.1 to 35.4, it is the moderate. It can harmful for our respiratory system, but it is not so severe. But if it is increasing more than 35.4 to 55.4, it will be sensitive to the groups that can make the heart disease. If it is more, suppose 55.4 to 150.4, it can be the unhealthy that can have the respiratory effect in population. And if it is more than 250.4, it is going to be the hazards, wherever the air quality index is around the 301 to 500. So, and that can affect the serious effects in the population. So we can see the PM 2.5 is a very dangerous pollutant that can be found in the air, and it has been generated from our cooking gas, from our smoking, and from our industry gases, and from the other aspects. Okay, so this can be the harmful for our air and from our environment also. So we need to address how we can make a sensor that can actually absorb this PM 2.5 contaminants in a more better way. And that is our task mainly. Using the nanomaterial, that is using the graphene nanoribbon, how we can actually make a sensor that can actually reduce the PM 2.5 contaminants in the air. So for that case, we have started our work with the graphene nanoribbon. So I hope that this term is very popular to all of us. So basically, the graphene nanoribbon was being first invented by the scientist Fujita, who was a Japanese physicist. So he was invented this term of graphene nanoribbon. And here, basically, the graphene nanoribbon is mainly uh, mm, basically a 2D like structure. We can see here. This is actually a planar shape structure, wherever the carbon atoms are bonded in a honeycomb lattice shape. Okay, so this GNRs is being very popular because it has a very high surface to volume ratio and it has a finite band gap over there. And as per the GNR, it can be differentiated in the two types, that is the chiral type and the achiral type. So basically, what is the chirality? Chirality is nothing but the cutting edges of the GNRs, because GNR is mainly a thin ribbon of the graphene sheet. Okay, so if we have a graphene sheet and whenever we are cutting a thin ribbon from this graphene sheet, it will making as a GNR. So depending on this cutting direction, it can be defined either as a chiral or it can be defined as either as a achiral. And chiral can be of the two types. Okay, that one type can be made as a zigzag, another type can be made as a armchair. We can see here the edges are basically showing as a zigzag type of the edges, so that it is called the zigzag kind of GNR. But wherever in the second figure, if you can see, it is showing as a armchair type. You can see this is the chair type, correct? That's why it is known as a armchair type of GNR or the AR GNR. So basically, both the type of the GNRs have their different properties, have their different aspects, have their different applications. Because based on these properties, we can have both the metallic and semiconducting properties in the case of the armchair GNR. So that's why we are basically using here the armchair graphene nanoribbon for our purpose. Okay, for our research, that is called the AR GNR. So before going to the AR GNR, we should have to know about the physics of the absorption. So what is the absorption and how this absorption is taking place in the case of the armchair GNR. So we can see the absorption is a process actually wherever it is being involved with the two components. One is the adsorbent and another one is the adsorbate. Okay. So adsorbent is what? Adsorbent is the substance on the surface on which the adsorption takes place, and adsorbate is the substance being adsorbed on the surface of the adsorbent. So basically, the adsorbent is the substance wherever basically we can make the absorption property, and adsorbate we can have it will be getting absorbed. So depending on this, we can get the absorption energy. We can calculate the absorption energy by using this formula given in the expression 1, wherever the absorption energy is equal to the total energy of the substrate or gas minus the energy of substrate minus the energy of the gas. So basically this so basically how this absorption are taking place. If you can see here, so if you can take a substrate, suppose that this is actually a armchair graphene nanoribbon substrate, okay, armchair GNR substrate. So this is, so here whenever the gas molecules are coming, so how they are going to be absorbed on the substrate, that we have to see. So if the gas molecules are going to be absorbed only on the surface region, that is called the physical absorption. And if these gas molecules are making some bonds like this, if they are making some bonds with the surface atom, that is called the chemical absorption. Okay, so basically depending on the absorption criteria, we can have either the physical absorption or the chemical absorption. In the case of the physical absorption, it may be somewhat unstable, but if we have in the chemical absorption, it will be very, very stable, because it will making some bond, and we all need this kind of the chemical absorption with the surface. So Depending on this basic theory, so this is our proposed research model. So wherever actually we have working on the graphene nanoribbon based gas sensor. So basically we are trying to make a gas sensor using the Armchair graphene nanoribbon. Wherever basically we are this is the flow chart. Wherever we are having the modeling of the graphene based gas sensor, that is if we are using the Armchair based gas sensor, so so basically on which side we have to getting absorbed and what should be the distance. So all these things we have considered for the modeling of the gas sensor. Then we are have the influence of the surface morphology of the gas sensing, then insights into the atomic scale transition, and that will be given with the influence of doping, the placement of the dopants, the influence of the wider and the narrowest edges, that is the edge effect we have considered in our work, and also we have considered the random dopant fluctuations. Okay, so basically these four factors we have considered for the analysis uh, of our gas sensor. And with this analysis we have trying to address how the PM 2.5 contaminants can be sensed or can be addressed using those gas sensors. So this is the first part of our research, wherever basically we can see either we can use the monolayer AGNR or we can use the bilayer AGNR. So where we can have the binding energy is more, or where we should have the binding energy will be less. Okay, so this is the first one. So here you can see this is this analysis has been done using the quantum-wise ATK software, wherever we can have the monolayer and different type of the bilayer AGNRs actually. So we can see the first figure, that is from A to D. These are the monolayer AGNR. That is so in this case of the monolayer AGNR, we have used, this is the pristine, that is the undoped monolayer. Number B is the boron doped monolayer. Number C is the phosphorus doped monolayer, and number D is the boron phosphorus doped monolayer. So we have used both the types. Either we can use the pristine type, that is the undoped type, and we have used the doped type also, like boron doped, phosphorus doped, and the boron phosphorus doped. Okay, so this is the monolayer kind of that GNR, that is single layer. After that, we have also going towards the bilayer. Why we are moving towards the bilayer? Because whenever the growth process of the graphene has been carried out during the fabrication, it is very difficult to generate a single layer of the AGNR. Okay, and that's why there may be the multiple layers. So that we have taken the bilayer type, and in this bilayer type we have trying to see with the AA stacked, okay, AA stacked, AB stacked, and the AB twisted stacking. So this AA stacked means that is here the bottom and top layers are aligned each other in the 90-degree angle. You can see here, there is no shift, only they are aligned with the 90-degree angle with the both the shifts. In the case of the AB stacking, basically here the bottom layer will be fixed, but the top layer will be shifted by some distance. We can see the figure here. The bottom layer will be fixed, but the top layer can be shifted with some distance. And in the case of the AB twisted software, AB twisted, the same thing, that is the bottom layer will be fixed and top layer will be shifted by some distance, but there might be a 5 degree of a rotation in the surface. Okay, so basically these three type of the monolayer and the these three type of the stacked bilayers we have addressed using the quantum wise, and after that we have done the analysis of the binding energy, and we have seen this table. You can see the table 4, wherever basically we can see the monolayer is the best configuration, wherever we can have the more binding energy compared to the all the bilayer type, but AA bilayer is giving you the basically the better result compared to the AB AB bilayer and the AB twisted bilayer. So in summary, what you can do, the AA bilayer still remains the better binding energy than other configurations like the AB and twisted AB bilayers, yet it falls short when matched against the monolayer. The monolayer AGNR benefits from the absence of the interlayer disruptions, resulting in a greater stability, making it far more effective than any bilayer configuration, including the AA bilayer. So basically, as per the physics, monolayer is the better one, best one. But if we are using the bilayer, then AA bilayer will be the better compared to the other type of the bilayer theory. Okay, so these things will be shown by my research scholar Mr. Kamal Solanki just after this session. Next one is that where we should make the dopant. Either we should make the doping at the edges or at the center of the AGNR. So that thing we have to see there. Okay. So for that case, we can see this is the illustration of the doped. This is the illustration of the AGNR. So this first figure, number A figure, is the doped AGNR, and this is the device structure wherever the electrodes are being fixed at the two sides. Okay. So here basically we have make the doping in the at the different locations. We have make the doping either at the edges or at the center. You can see the number A and B, we are actually having the doping either at the zigzag edges or the armchair edges, and here basically we are make the doping at the central region. Okay, so this is the doping at the central region of the boron site, and this is the doping of the central region at the arsenic site, and then we have made the device model, and then we have made the comparison using the QuantumATK tool, and this is the IV curve analysis for both of these. And if you can see this IV curve analysis very minutely, we can see in the first curve, that is this number A. Here actually we can see the current is more for the pristine AGNR, that can be without gas absorption. But whenever we have the gas absorption, that is we are using the NO2 absorption, that is the NO2 absorption we are using here, and after the NO2 absorption we can see the pristine performance is very low, correct, and we can have the best performance in the B side BN dot AGNR, you can see. Okay, so it means that doping is always better compared to the pristine structure, and if we having the doping at the B site in the BN doped AGNR, it will be the better one after the gas absorption. And we have also analyzed our results like that. In summary, compared to the undoped AGNR, the boron phosphorus and boron arsenic doped AGNR structures demonstrate a remarkable near the 100% response after the NO2 absorption at the B site, and approximately 45% and 55% at the phosphorus and arsenic site respectively. Okay, so this is a very interesting result that we have observed from the QuantumATK software. Next, we are trying to address the width-induced electronic shift. That is, we are trying to use here the narrowest, wider to narrower. There is narrowest AGNR. Actually, there is no term like the narrowest, correct? So, but depending on the literature, we can use the term as a narrower AGNR. So we can see here what is the advantage if we can use the narrower or the narrowest AGNR. So the advantages are that we can have the strong quantum confinement, we can have enhanced interactions, we can have the enhanced spin effects and the surface dominated behavior. And we can see here this table here basically we are using the different width of the AGNR, like width 3 to width 9. Okay, so we can see here if we are going for the narrower or the narrowest, that is in the width 3, we are having the absorption energy will be more, and the percentage band gap we are having also the 60.47 percentage, that is before, and if we can compare the before absorption band gap and after absorption band gap, then we can have the percentage band gap, the difference is 60.47 percentage, and that is a very good thing for our device application, that is the sensor applications, correct? So that's why if we can use the narrowest or the narrower kind of the AI channel, it will be always better for the application. So depending on the existing literature, we have tried to address um, for the different width. Okay, so that is from width 3 to width 8, and we can get in these results, and after the width 8 basically it can be somehow increased. But depending on the existing literature, we can conclude that our width 3 will be the best one for the narrowest air channel. Next, and the last one we are going to show, that is the revealing the conductors transition in AGNRs with a random dopant effects. Okay. So here basically what we are trying to do, we are basically using the different sites of the ARGNR. So this is suppose the pristine ARGNR. So we are using the different sites like C1, C2, C3, C4, C5, and C6. Okay. So now in these different sites actually we have made the dopant at the boron and the phosphorus. Like suppose in the first figure we are having the boron at C2 and phosphorus at C3. In the second figure, boron at C2, phosphorus at C4. In the third one, boron C2, phosphorus C5. So this way, basically, we have fixed the boron atoms and we have tried to circulate the phosphorus atoms at the different locations. Okay, and after that, the NOP absorption has been taking place, and we have seen if we can make the boron and phosphorus dopant at these edges, because this is called the armchair edge, correct? This edge, that is C2, C3, or maybe you can say the C5, C6. These are the armchair edges, and this C1 and C4 is the zigzag edges, correct? So if we are making both the dopants in the armchair edges, we can see it will be the good for the application. Okay. So here basically this is the results. Basically we can see the boron atom we have fixed at the C2 location, and phosphorus atom are being getting transited at the different location in the case of C3, C5, C4, C1, and C6. And we can see if we are having the C2 and C3, after analyzing, we can have the current change is around the nearly is around the 2.32x, which is showing the strong charge transfer, minimal strain, and the efficient transport phenomenon using this material. Okay, and this is the IP characteristics for this, and you can see actually in this curve we are showing the two things. One is the with NOP absorption and without NOP absorption. Okay, and you can see with NOP absorption and without NOP absorption, which one is the better one. Okay, so this way actually we can have which site will be better for the boron and phosphorus doping for our sensor designing. So all this type of the analysis we can do using the quantum-wise ATK software, and using this analysis we can make our sensor for the further designing purposes. And this will be demonstrated by just after this session. So this is about the insights of this transition behavior, the same thing that already I discussed, the structural stability that we have discussed about the monolayer versus bilayer. So which one is the better, we have seen over there, correct? So in basically monolayer is the favorable one, but if we can use the bilayer, we should use the AA stacking of the bilayer. Device optimization via the central doping. So doping at the center of the GNRs tends to the stabilize of the device properties. So doping at the center is always better. In the case of the width engineering, if we are having the narrower AGNR, it will provide the more pronounced quantum effects. So we should always use try to use the narrower AGNR. And fourth one is the dopant engineering, the position and type. So that already we have seen how we should make the dopants, and in which sites, like in the C2 and C3 sites, if we make the dopant, it will be the more stable out of that. Okay, and this controlling of this, but here some of the challenges are there. That is in the first case, that is in the structural stability. The challenge is that it is very harder to transfer without additional support okay, limiting the integration in the devices. In the second one, it will be the achieving of the precise central doping is also being challenging whenever we are using the bottom-up growth approach. In the third one, the fabricating of the narrowest AGNR or GNRs is being challenging, okay, because edges are very closer to each other. And in the fourth one, in the case of the dopant engineering, the controlling of the dopant accurately placement of that dopants are also very challenging using the fabrication methods, because we are mainly using the LPCVD or the ion implantation methods, and using these methods it may be a challenging for our dopant engineering method. And finally, these are the conclusions of this topic. So basically, we can see, as I told you, that the monolayer configuration can exhibit the highest binding energy. Placement of the doping at the center of the ribbon can result a more stable structural structure. And as the width of the AGNR is decreasing, significant electron shifts can occur. Okay. But it is good for the good absorption energy. And the monolayer stability. So basically, all these findings are highlighted the importance of the monolayer stability, the dopant placement within the controlling the structural and the electronic properties of the AGNR. Okay. So these all are crucial for the tailoring of AGNRs for advanced application in nanoelectronic and the materials design. So these are some of the key publications that actually we have achieved from our research group, okay, using the quantum-wise Atomistic toolkit software in the last 3 years. Okay. And these are some of the references that we have followed for this work. And thank you for your patience. Thank you.
Thank you, sir. Thank you for this nice presentation. So, if anybody has any query regarding this presentation or for this Graphene Nanoribbon, so you can have a discussion with this, sir.
Yeah, I think there will be a demonstration, hands-on demonstration by
Yes.
scholar.
So, before going demonstration, sir, if
Yeah,
anybody
so
has any
maybe
query,
after
they can ask
demonstration,
with this, sir.
the candidate has some question, we should have to address. Okay,
Yes, sir. Okay.
thank you. So now I would like to request Mr. Kamal Solanki. Kamal, are you there?
Yes, sir.
Yeah, you please start the demonstration
Yeah. Yes.
for the participants, please.
Yes.
Thank you.
Hello, good afternoon, everyone. My name is Kamal Solanki, and I am a PhD scholar in the Department of Electronics and Communication Engineering, IIIT Raipur, and currently working under Manoj Kumar Majumdar, sir. So today I will actually demonstrate the QuantumATK software and for the gas sensing application. And the material I will opt, that is the Armchair Graphene Nanoribbon, and I will show you over there why I am taking the Armchair Graphene Nanoribbon for the gas sensing application. So Deepak sir, can I start?
Yes, sir. Sure. You can start this, sir.
Yes. Are you all getting the picture like that?
Yes, sir. Yes, sir. Your screen is visible to all of you.
Yeah. Okay. Thank you, sir.
Okay.
So before starting the live demonstration of this QuantumATK software, I want to ask you all, how many of you are actually working on the gas sensing application? You can share your perception here, so we can discuss accordingly. Because this is not just only the demonstration, we have to also discuss the ideas. Maybe your ideas will help me, or maybe my idea will help you for your further research work. So any suggestions, or anyone, please? Or I start? Yeah, hello. So can I start?
Yes, sir. You can start.
Yeah.
I think there
Yes,
is
sir.
no suggestion from anyone.
Yes, sir. So here is a QuantumATK dashboard. So I think so that is the latest version compared to the previous one. So here you see that in this dashboard there are the data filters, data sources, and the data view. From the previous version, it's not having the same dashboard like this. So what this benefit in terms of less complexity and all that. So here you see in the data filters, everything only data, no script logs, only script, molecular configuration, bulk configuration, device configuration is there. So here are the data view. Here we can see the results, what we have actually calculated from the tool, and here are the data sources. So what we actually calculated from this tool. So suppose if you want only the bulk configuration of over here, you can just click this bulk configuration here. You will see all the bulk configurations of the material which we have calculated from the builder tool. We can able to see it here. Suppose if you want to see only the script, that is the Python script, so it will be appear here. For the device configuration, you can see all the device configuration which we have made from the builder tool. It will be appear here, so you can directly view or you can see the results from here. So this is the general dashboard of the QuantumATK software in the data part. Now we'll go towards the builder. So in the builder section, this is just a few few materials or structures which I have made to demonstrate you. But before telling you about this, I am going towards giving you the overview of this dashboard of the builder tool. So you can see here, these are some of the various configurations, how to change this configuration using all this thing. So first of all, you can see here the square box is there. It is actually showing to select this atoms. So just if I will select the circle one, you can see if I will scroll here, it will move towards in a circle shape and we can select all the atoms. So I think so before giving you the description about this, I will go towards how to create this actually ribbon. So you will get the better understanding of this. So in the plus sign, you can see the new configuration from files, from database, from plugin, and from clipboard is there. So you have to go towards from plugin. Here you see that there are the various materials are there like nanotube, crystal builder, nanoribbon, nanosheet, magnetic tunnel junction. As from the previous presentation, you saw that our area of interest was the Armchair graphene nanoribbon. So currently I'm opting for nanoribbon. So here is the nanoribbon which is having the chemical properties carbon-carbon. Suppose if you want to change the chemical properties like from carbon-carbon to somewhat different, so you can just click here and you will able to see the periodic table over here. It is showing all the materials over here. So suppose if you want to do with some other material, you can select, just for an example, I'm selecting the nitrogen. So you can go for the nitrogen carbon nanoribbon. So it will appear like that. But for the Armchair graphene nanoribbon, mostly we have to select the carbon-carbon. So I am opting again for the carbon. So here the chemical property is carbon to carbon with a bond length of 1.42 angstrom. Here you see that here it's a tick mark is there. Actually, it is showing that that Armchair graphene nanoribbon will be passivated by the hydrogen atom. And the geometry here shows the aligned unit cell with chiral vector, zigzag edge, armchair edge. So from the presentation, you heard that graphene nanoribbon is having two types. First one is armchair, second one is zigzag. So depending on the application, we can opt for this structure. So listen carefully. I am working towards the gas sensing application. So mostly in the gas sensing application, there are two cases: before adsorption, after adsorption. So mostly we are focuses on the electronic property, that is electron density, density of states, what to say, band structure. So band structure we are getting before and after adsorption. So we are actually checking how much the band gap is varying before or after adsorption. So the Armchair graphene nanoribbon provides us the better property like metallic or semiconductor band gap variation. This is not same possibility with the zigzag structure, because in the zigzag, because of the edges, the edges are over like this edges actually providing the metallic property. So mostly zigzag is used for different application, but Armchair is mostly used for the sensing application because it provides the band gap engineering. So here I am opting for the armchair edge with atoms wide. So here 4 atoms, so we can change here the number of atoms. So I am currently opting for 4. So here you see that the 4, like with 4 armchair graphene nanoribbon is there, like 1, 2, 3, 4, and these are the passivated hydrogen. So now here I told you about this. So you can opt for the square one. You can select the number of atoms from here like this. Okay. And why the selection of atom is required, I will tell you in the subsequent part. So from this, you can able to measure the distance. How much distance between the carbon to carbon bond is there? Like this. So mostly in the graphene or graphene nanoribbon, C to C bond length is 1.42 angstrom. Okay. And from this, we can, like as you heard that we are working towards the gas sensing application. So when I just put my mouse over here, you can see that we can build molecules by adding atoms, bond, or fragment. So here from this we can select different gas molecule or different gas molecule for the sensing application. There are the various molecules present over here, so we can select any one of them for the different applications. So we will cover soon. From this, we can able to see the configurations and how much atoms is there in this dashboard. Like it's showing the 12 atoms, lattice type, unit cell, its primitive vector, its volume, density, reciprocal vector, and all that. After then, here you see that one passivation is there. So it's showing that passivate the configuration with hydrogen. So just suppose I am clicking this atom, and here you see that it gets enabled. So why it is enabled? Because I have selected this atom. So if you want to remove this atom, you can just click here. The atom is removed. And suppose if you want to again passivate this carbon, then again click here. Then again just click here. So here what is actually it is showing? Passivate the configuration with hydrogen. So you can click here. The hydrogen passivation will be there. So after then, suppose if you want to dope this armchair graphene nanoribbon, so just select the atom. Here you see the periodic tables get enabled. Just click here and you can select any one of this. Suppose mostly in the previous literature, I saw that they are preferring over the third and fifth group element. So I am just going towards the third group, that is boron. So I have selected boron and just place over there. So nothing changes. It's mostly called as the substitutional doping. But only the configuration, the boron is there, but you can also change the concentration. So just click here. Here already it is there. So just I'm removing it and I will again type it. So from this part, you can write doping. So in the doping, you can select it and the atom is already selected. Just put or like press the button add. So here the doping is there. You can edit it and write boron. Impurity doping type is P type, and here is the value. So you can change this concentration by seeing the literature review and just cut it. So the concentration will get enabled over here. So you see that. Suppose if you want to remove, just press the remove button. So this is how you can do the doping in any material, not for the case of armchair graphene nanoribbon, but for also the different materials also. Now again, I'm selecting this. It's a square box coming. You can see that here it's showing that add a small random perturbation. So if I'm clicking over here, you see that the perturbation is creating over the armchair graphene nanoribbon. So see how the structure is getting perturbated. How we can see that the structure is perturbated? We can see by measuring the distance. So just click over here distance and you can measure. So the question again comes, why the perturbation is needed? Why the perturbation is needed? Perturbation is needed. Suppose if you are experimenting some material for the sensing application, and during the growth of during the formation of epitaxial layer, maybe some deviation between the bond line take place. How that deviation leads to affect the sensing properties. So we can even imagine through this perturbations concept. We can also perturbate the system without optimization also from this QuantumATK builder section. So again, if you want to undo this structure, then click this undo. So structure is here with us. Again, select all the atoms. You can see here this it's like for reducing the unit cell. Again, already the atom is selected, but still we can change the symmetry of this using this. This is the camera. You can change the lattice plane. Mostly we go towards the BC, AC, AB, CA, CB, like that. So this is how this all things are working. In that somewhere some part is also there, like this three, but this may not enable right now, but we will focus, we'll see after that. And see, for this case, if you select this, then you see at the bottom here, it's showing that no overlapping atoms are there. Sometimes overlapping may happen during the creations of material, so we can check with this. And already this is the undo and redo for this structure. So this is the structure. So this is all about what is Armchair graphene nanoribbon, how it is created, how to measure the distance, how to see the number of atoms present in the builder section, and how to passivate this, how to dope this with some doping concentration, how to perturbate this structure, and how to see the camera properties. We can see it any direction, how the atoms are arranged in the unit cell after them. So are you all getting my voice? Can anyone? Hello?
Yes, sir.
Yeah.
Yes, sir. You are audible.
Thank you so much, sir. So this is all just creation of the bulk configuration of Armchair graphene nanoribbon material. Now I will show you how to create the device from this material. So this is the structure. So again, if you want to see again how to create the Armchair graphene nanoribbon, let's see it from the plus sign. We can go towards the plugin. We'll go towards the nanoribbon. We can opt for any atom width. Let's go for the 6 atom wide or maybe 5 atom wide. We can build this structure. So we have built this structure. Then we see here, yeah. So this is the configuration. So what are the steps we have to follow for creating the device? Just see step by step.
Can you just repeat it again?
Should I repeat, sir?
Yeah, just repeat it again.
Yeah, thank you. So again, I am deleting this. Oh, no way to delete it. I am going towards this plus add sign. I just click it. From the plugin, I gone towards the nanoribbon. In the nanoribbon, we are working towards the Armchair graphene nanoribbon, and I am making the device of Armchair graphene nanoribbon device structures. For that, from this 3 geometry, I am selecting the Armchair edge with 5 atom wide. You can go for any width depending on the previous literature, or you can go towards the random widths and see how the variation in widths influences the electronic, chemical, or optical properties. So currently I am going towards the 5 atom width Armchair graphene nanoribbon structure. So I have built that structure. This is the structure. So before going to create the device, we have to repeat this structure. For that, I will write here repeat. So you see that repeat is there. Choose the number of times the configuration should be repeated along the ABC axis. So you see that ABC axis is there. So I have to repeat this structure towards the C direction. I will tell you why I am repeating towards the C direction. Let's go 2, 2, 2 at all 3 sides. I have applied it. So you see that here the structure got broke. But in the C direction, structure is not getting broke. Why it is happening? Because our structure is periodic in C direction. Periodic means it is repeating infinite times over there. But we cannot measure the electronic properties of infinite number of atoms. For that, we are going towards the less number of atoms to see how it influences the electronic properties. So right now, I am going towards just C direction and repeating this structure. Maybe around you can repeat it 3, 4, 5 times and you can see how it influences the electronic property. But right now I am going towards 3 and we'll see whether the device is forming from this or not. So I have put it here 3 and it is repeated 3 times. If you want to see how many number of atoms are there, you can just click here and you can see that 42 numbers of atoms are there in the bulk configuration. So now you can go towards device from bulk. So you can type here device from bulk or directly write device. Here it is coming device from bulk. Click it here and you see that it's showing the dashboard of device from bulk property. You see that minimum electrode length 4.26 angstrom, electrode extension length. Why extension length is here there? Because to overcome the physical effect, means there will be no effect of electrode in the channel material. For that, electrode extension length is required. So you can change this also. Suppose I am putting it 2, but here the perturbation is happening. That's why we are not putting it 2. We are putting it to, suppose, going towards the 8. Then you see the error is coming. The sum of length of electron may not exceed the length of central region. So we have to go for the 4 angstrom. You see that the channel material is there, electrode extension length is there, 2 electrodes are there. Just press the OK button. So here is the device configuration of Armchair Graphene Nanoribbon. So yeah, so this is the structure. And suppose structure is created, everything is done. Now if you want to optimize or you have to calculate the electronic property of this device, just directly go towards this here, towards the workflow builder. So in the workflow builder, that is the device. So you have to go for the device LCO calculator. Device LCO calculator, and as you know that whenever we are solving any structure, we have to optimize that structure. So if the device is not there, then we have to go for the optimized geometry for the bulk configuration. But if suppose the device is there, then we have to go for the optimize device configuration. Here it is. So double click it. Here the optimized device configuration is there. Now device is there, optimized device configuration is there. Now we have to check which analysis we have to perform using the quantum-wise ATK. So here are the various analysis there. So mostly for the sensing application, I am focusing towards the IV characteristic or IV curve analysis. So here is the IV characteristic. And there are a lot of electronic property that we are actually measuring for the device configuration, like device density of a state, how the electron density take place, transport phenomena, what is the effective potential of that device band structure, all that. But right now I have just opted for the IV characteristic. And in the set device LCO calculator, I am just clicking, double click. So here, set device calculator dashboard is open. So here are the various parameters which we have to opt for calculating the device Armchair Graphene Nanoribbon. So here the basic parameters are there, numerical accuracy is there, and the populate key points are there. So without not taking too much time, I will give you the short overview how you can select this parameter. First, you can opt for any parameter and you can see what electronic properties are you getting and how it influences. Means suppose if you are taking the spin unpolarized, there are the various points here. But if your material is exhibiting some magnetic property, then go for the polarization. But if it is not, then go for the unpolarized. Exchange correlation is GGA here. Here the various exchange correlation is there from LDA to the hybrid custom. So from the previous version, from the previous literature, most researchers are using LDA, that is local density approximation, that is actually used for providing the accuracy in the algorithm. But I am generally opting GGA, and also the literature right now it is coming that showing the GGA, that is generalized gradient approximation. Actually, this is just not including the density, electron density, but it also including the electron gradient. Gradient is also including it in that approximation, so that it calculates the fine-tuned electronic properties. And suppose if you are moving towards the MGGA, then it including the kinetic energy. So electron density, then gradient, then kinetic energy. All three will come into the picture and make the electronic property more accurate. For the pseudo potential, we are using the FHI. As in the presentation, it was there. That is actually we are opting this to take the core electron, and also the core electron of atomic orbital. And for the basis set, double zeta polarized, I have opted single zeta polarized is there. But what is that double zeta polarized is actually comprises that we are not only opting the nucleus, but we are also opting the outermost shell electron with the nucleus for calculating the electron density of that complete atomic orbital with the help of linear combination of atomic orbital calculator. Occupation method is Fermi direct, broadening is 1000. Broadening is actually defined as pulse spreading. So you see that in the density of state you are getting some peaks. Sometimes it is get broadened, sometimes it's not. Sometimes you are getting the discrete states. But if you are giving the broadening temperature, so what happens? It provide more sharp discrete states. But if that broadening is less, then it will provide some broadened peak. You can analyze by changing the broadening temperature. Density mesh cutoff, it's like the grade for the electron density, and K point sampling. Here you see that it's automatically showing A, B, C with 150. Why it is showing more K point sampling towards the 150? Because our structure is periodic in the C direction and it is repeating over infinite times, but we are opting for the less number of atoms, that is 42, as we see that in the configuration side. So that is less, but atoms are more in that direction. That's why we are opting more K point sampling towards that and not in the other cases. And these are the electrodes. Suppose if you want to give some voltage, you can opt for like even if you can take right voltage or left voltage. Just I am giving the right voltage. So these are the main parameters for there. Just cut it here. Right now, these are also some of the parameters of the device also calculated. That is going towards the more deeper towards how the analysis get varied while changing the different parameters. But for that, I'm going towards this iteration control. You said that here no SCF iteration is there, self-consistent field. For that, the tolerance is defined here. So sometimes some researchers not opted for this. They can click here no SCF iteration, but we are going towards the SCF iteration because it will provide the new electron densities. They will not assume the previous old electron density, but it will measure again new electron density that can give better electronic property. Better electronic property means better variation in the band gap, better variation in the band gap values, better variation in the total energy values, how the structure will get very less value, like how much your structure get stable with these properties. From the optimized device configuration, these are some of the parameters over there. For this, here just you see that perform device optimization, we have to click this. So it will optimize the device. Why optimization is required for this device? Because optimization is required for converging the structure. Why convergence is required? Because if the structure is converged, it means it is indicating that whatever distance atom want to perturb, it is perturbated if the device is optimized perfectly. That's why optimization is required. And for the force derivation, here is the constant value is there like 0.05 electron volt angstrom per angstrom. That is showing that how much force will act towards that surface atoms. The number of steps is 200, step size 0.2, optimizer is LBFGS, and fire method is also, fire algorithm is also there. What is that maximum number of steps? That is 200. We can also write it 1000. Why I am changing this? Because if your structure is not optimized within 200 steps, then your QuantumATK will show that your structure is not converged and it will show the like wrong electronic properties. So within this step, your structure has to be converted to get the more stable structure. Then this in the IV characteristic, you see that there are the various parameters: gate to source voltage, drain to source voltage. But you see that in the builder section, I have created the device, but I haven't opted for any dielectric or the gate material. I haven't opted. That's why you see that in the in the workflow, you see that gate to source voltage is there, drain to source voltage is there. So we'll not focus in these voltages, we will focus towards the drain to source voltage. So mostly we can opt for 0 to 1 with points. Maybe you can take up to 10 points for better identification of the IV curve analysis. So just all things done. For the transmission spectrum, already all things are selected. But if you want to see some changes, then you can vary this self energy calculator or storage energy. But you can see that in the most literature, whether it is for the thermoelectric property, whether it is for the hydrogen storage application, for the electrocatalyst application, for the sensing application, none of them are actually showing this type of values over there, basic parameters and all that. Everything is not there, but we have to change this parameter and see how this affect the properties. So for that, you can change the optimization step, and with the less number of steps, you can see how this influences the electronic properties. So all three are selected. We can go for towards the job as script. You can say that press the OK button. I'm just saying towards my QuantumATK project. Here I'm going towards the threaded process, single process, and we will go towards the let's automate, and we can increase the number of thread towards the 5, and we are adding this structure. So my structure is over here. So just I am clicking it and I am pressing the run button over here. So here you see that it's showing the start selected jobs. So my job is already there. So currently I'm not just putting it on because it device time will get slow, like maybe quantum-wise will get somewhat like lag. So here you see that this yeah, I have optimized one device in the morning. So you see that optimized device configuration study. See, 4 tasks will be executed: convert device to bulk, optimize bulk, convert bulk to device, perform final device relaxation. So this optimized device configuration is actually executing the 4 tasks. First, what it is converting device to bulk. Device to bulk means it is converting that device structure to the bulk configuration with the mathematical parameters. And this optimized device configuration with the LBS-DS optimizer, they are actually optimizing that bulk configuration, again converting that bulk to device and performing the final device relaxation. So this is how the device will get optimized. So from the data section, we will see one result I'm having. I'll show you over here. Yeah, here it is. So this is the IV curve. Yeah. So I have selected this IV curve here. You see that here the open terminal is there. You can click it here. Open with IV characteristic analyzer. So I have clicked it, and here is the IV curve of that 2 terminal device. It is showing from 0 to 1 volt. As you saw that I am selecting there like drain to source voltage 0 to 1 volt, and the current is there. So from the 0, it's showing some 0 current, but when the threshold reached over there, then the current is increased over this. So why I'm showing this IV characteristic curve to you? Because during the sensing analysis, we are seeing that before the adsorption, how my IV curve is there, and after the adsorption, how my current is changing. So this current variation is totally depend on the band gap variation. If the band gap is decreasing after the adsorption, then the current will automatically get increased, because band gap is directly related with the conductivity. If the band gap is decreasing after the adsorption, then the current is increased, conductivity is increased. So this is the way to create the device and perform the device simulation. Now I will show you how to add molecule in the configuration. So again, I am going towards this add sign, from plugin towards the nanoribbon. Again, I am opting for the width 5. Let's see what is showing in the preview. Okay, like this, you can see that bond length is 1.42. I am going towards the build. Okay, so this is my Armchair Graphene nanoribbon with width 5 structure. So now I am going towards the adsorption. So I'm going towards this adsorption. So it's showing here. As you see that my structure is showing in the vertical direction. Vertical. But suppose if I want to adsorb one molecule over here, then how I will able to do it? So just I am giving you one important concept for the gas sensing application. Just see here in the drop zone, it's showing, and here also it's showing that C is in the vertical direction. A is here, B is here. Okay, but You see here, A is in the vertical direction, C is in the horizontal, and B is over here. So just cut it. Again, from the camera property, put it here, BC. Yeah. Now just rotate the structure, select the atoms, go towards here, just press rotate. It's already presetted over here. Mostly we are going towards the rotation axis D with the 90-degree angle. Just apply. Our structure get rotated by 90 degrees. C is in the vertical direction now. Now, as you see that vacuum is here. So what we will able to do here, go towards the lattice parameter. In the lattice parameter section, just change this A with C, C with A. So we can write here 4.26258, and here you will write 10. As you see that my structure is gone to outside, so for that you have to press here center, apply. So your structure is in the center. Now you can go towards the adsorption. So adsorption is here. Yeah. So here is the structure, and you see in the blue color line showing the no adsorption sides. And this one is showing the surface depth. This one, surface depth. Grouping precision, it means how your atoms are arranged in the unit cell. Go towards the recalculate adsorption side. Automatic, it's enabled. Just click here. You see that showing site types. There are number of sites are there. So what is all that? So here you see that this atom, if you will adsorb in the top of this atom, then it is called as top site. If you will adsorb in this site between these two atoms, then it is called as bridge site. If you want to adsorb some molecules over here, then it is called as hollow site. So mostly in the the researchers are like putting the gas molecule towards the top sites. So we are opting for the top sites here. You see that the 4 points get enabled. As you will see why these are not enabled. So for that you can go for top site C2. Again top site C0. See, all the sites are get selected, but where you want to adsorb. So in the previous presentation you saw that one research is there where to dope, central or the edge region. Mostly the central region is used for the doping purpose. So in the central region we are opting for the top site for the gas sensing analysis. So now I am opting towards the C1. Okay, I am going towards C2. So here from this, this is the pre-made molecule. I will also show you how this molecule is created. So just click here, drag your mouse toward here, put it here. Your molecule is added, but it is not showing here. Why? Just show the site type, click here. I have opted for the C2. Just click here, C2 site. Your molecule is here. You can change the distribution. You can change towards S1, S0. It's your perception. You can see how the varying the site impact your electronic properties. You see that count and occupancy is there. Occupancy is generally defined as how much this molecule takes the fraction of that unit cell. That is defined by occupancy. Height. Height is actually this one, this adsorption site height. So one query from the audience section I got that is there any bond formation required for this sensing? According to me, I will say no. There is no requirement that bond formation will take, because in this already there is some bond between this, but we will not able to see this from the naked eyes. How I saw, because when I am calculating the electronic property, I saw that the 2 angstrom height is showing the best optimal adsorption site for the gas sensing analysis, and we also evaluated through the IV curve analysis. So that's showing the better electronic property. That's why 2 angstrom is the optimal one. Out of 3, it will be like there is adsorption get difficult. So we have to opt only for the 2 angstrom so that the adsorption and desorption both take place. New configuration here. You can rotate the molecule from here. Different orientations are there. Custom rotation, but I'm focusing. Yeah. We have. Let's see here. I think in one case the bond formation took place. Yeah, you see that here. the bond formation take place, but this is not required. And you can also see the anchor atom is nitrogen. So you can change anchor atom hydrogen. You can change anchor atom to hydrogen, second hydrogen, third hydrogen. But mostly we are going towards the nitrogen. And we will go towards the vertical one. Just go and press the create button. So here your structure is ready with us. This one. So this is the Armchair graphene nanoribbon with ammonia molecule. You can see the distance from here. How much distance is this? Where it is adsorbed here, like this. Yeah, 2 angstrom is there. So one thing I would like to tell how this NS3 molecule get created. So see here. In the initial, during the initial time, I told you that you have to build molecule from this. Just go towards here. Just see where the ammonia is here. So it's the hydrocarbon, basic organic group ammonia is here, like that. But we cannot directly go towards this first. Sorry for this. We have to go for plus sign. We go towards the new configuration. Here is the new configuration. One atom is there, that is hydrogen atom. Now go towards the build molecule. Already here ammonia is there. Just go and click it here. Your ammonia is ready. What we can do more from this, like go towards the static bond, and you can see you can also change the bond distance or also change the bond angle from here. So mostly in the research papers, whatever molecule they are taking for the gas sensing application, they are generally defining what's the bond distance, what's the bond angle between that. But suppose if you go towards some novelty, then better to go for some other distance or other angle and see how the variation in angle influence the electronic property. So just it's completed. Again press this. So your ammonia molecule is ready, and you can even rename this by writing here at ammonia. So this is how we can create the molecules. Now last I would like to give one more information that how we can add molecule to device. So again go towards the plugin nanoribbon. Again I'm taking the 5 width. Here it is. Now first go to repeat the structure. I am repeating this structure 3 times in the C direction. Now as I already told you, when we are adsorbing some molecule, then we have to tilt it. Select the atoms, go here, write rotate with 90 degree. Okay, some O atoms are closer and some atoms are overlap. No issue. Go towards the lattice parameter. You can change. You have to change the lattice parameter. So here it is 12.7877, and I'm just shuffling it now. Here it is 10. Okay, that's done. Now right here center. Okay, now it's in the center. Now go for the adsorption. Adsorption. Here it is. The adsorption is there. Yeah, here is the configuration. Recalculate the adsorption site. Go towards any sites. I'm going towards right now. Again, going for the C2. Allow for the center site towards the C2. Distribution, you can opt for any site, site 3, site 4, yeah, site 4. And again, I remembered one question from the audience side. One asked me, can we sense this molecule towards the electrode region? I will say definitely no, because in that the interface state is also there, and the electrode task is to inject the charge carrier from that part to the central region. So influence of the gas molecule over there is very not useful over there. That's why we are like putting this ammonia molecule towards the center only for the sensing application. So mostly you have to go for the center doping or the center like molecules. Suppose why I'm always telling it center, because if you have created the device via the experimental method, so what you will get the electrodes, you will get the center region. Your molecule will get adsorbed toward the electrode region, but your like IV analyzer will not show any curve. But when it will adsorb in the central region where the channel region is there, then it will show some of the property over there, how the current is getting perturbated with the presence of external perturbation like this ammonia molecule. So you see that occupancy is now increased. It's showing the fraction, how much fraction this molecule is taking towards this unit cell. Adsorption height is 2 angstrom. I'm taking vertical, everything same, great. It's created. Now just what to see here, just select this atom, go again here, okay, select here, go again, rotate D at 90 degree, 1, 2, 3. Again go towards the lattice parameter. Now you have to change this. How I will remember this value? I'm writing this right now here, 17.3561, and I'm writing here 12.7877. Here I'm writing 17.3561, and now I will write here 0. It's done. Here it is. Now just write here center, apply. So it's all created. Now go towards the device from bulk. Yeah, so here it is. Here some perturbation is there, you can change it by here. But yeah, something is happened. I will tell you why this is happening. You see that extension length is here 4.26 or electrode, both the cases it's same. But you see that these 3 molecules are coming over here. Why it is happening? Because this electrode extension is actually hampering this molecule. That's why this edge is actually spreading over here. That's why the molecule is also spreading here. Just create it. Okay, now it is coming here. So if you want to avoid this, what you can do, just again go to the plus sign from plugin, plus sign, plugin, nanoribbon, 5-bit, go towards here, repeat. I have opted for 3, go for the 4, this one. If you will go towards this, like repeating it 4 times towards the C direction, then that problem will not be there. So this is how you will add the ammonia or whatever, like methane, carbon dioxide or any molecule to this surface. So I will just show some of my research. You saw that in the presentation. This is how the QuantumATK tool is working for the bulk configuration, also for the device configuration. As you see that I have created some structure over here. As you see that my first research, that is mono layer or the bilayer. So which structure is best, monolayer armchair graphene nanoribbon or bilayer armchair graphene nanoribbon? So you see that here. If I will press something like this, just see. See, my bottom layer is here and my top layer is here. So this is the AB stacking. AB stacking means the bottom layer is somewhat fixed, but the upper layer is shifted by some distance. If I will go here, then you see that, see, some bottom layer is fixed, but the top layer is rotated by some angle, that is called as magic angle. Magic angle you can opt for any, and you can also see the literature for that. I have opted for 5-degree magic angle. So, and this is the AB stacking. The bottom and top layer is aligned with each other like this. Let's see, I am doing one thing. What will happen? Yeah, see how the bond formation takes place and how the bond distortion takes place. So you can vary this, and you can also go for this and see how the electronic property get affected. So these all are the bilayer structures, and what I am creating from here, from the nanoribbon, like this armchair graphene nanoribbon and this one, and suppose if I am repeating this structure, so this is the monolayer structure, and this monolayer structure is the first outcome of our work, that it shows the better sensing property towards the different gas molecule compared to bilayer armchair graphene nanoribbon. Why it is showing the better sensing property? Because it is having the better surface roughness compared to the bilayer AGNR. That's why we are opting this for the gas sensing application. So this is from my side for this QuantumATK tool. And one thing I would like to also add here, that these all are some of the computational details which I am provided to you, and also I am doing this for the analysis of sensing, like different gas molecule or something like metals and all that. So someone asked me how this is possible towards the practical sensor. So I will say there are the few steps we have to do to making this real-time sensor. So first we have to create the graphene through some instruments like LPCVD, low pressure chemical vapor deposition. So right now I am growing the graphene towards the LPCVD instrument, and after creating the graphene I will go to make that graphene into graphene nanoribbon. Then we'll go towards the electrode creation. After that, for the sensing analysis, with the help of gas sensing instrument, we'll purge some gas molecule over there and see how it influences the electronic property. So the road is somewhat difficult, but we'll try to do that. And again, one thing, why I'm using this software for the sensing analysis, because QuantumATK actually provide, see how, suppose you have created the device and after giving your 8 to 9 months, you are seeing that your device is not working. So what you will do? You will do nothing. But from this tool, we can able to see how one defect can distract the electronic properties, and how one perturbation, how the perturbated structure influences the electronic properties like band gap, adsorption energy, total energy, desorption, whether the desorption is giving or not. All things we can study from this tool. So this will not solve the real world problem that is going towards us, but this will give you an idea how to solve this problem, and you will even imagine how the things will get work when we will go for the device creation. So thank you from my side. If any question is there, you can ask. If the question is, if I will able to tell, then definitely I will inform you about it. Thank you so much.
Yeah, thank you, sir. So if anybody has any question, so they can ask with this, sir.
And even if you are asking, then it is well and good. And if you are not, then I'm sharing my email ID. You can ask your query over there. I will try my best to solve your problems. That email ID is kamalsolanki033@gmail.com. And once again, thank you Integrated Microsystem for giving the opportunity, and thank you Deepak sir for helping me towards this QuantumATK software on a monthly or whatever basis. Your support is so much meant to me. Thank you so much.
Okay, sir. Thank you
Hello,
so much.
Mr.
So
Kamal.
this session is
Yeah, I think one question is there. Please,
Yeah,
sir.
I have a question.
Yeah.
So when you're building the structure for the sensing purpose,
Yes, sir.
the periodicity is removed in all directions, correct?
Again, sir, please, sir.
Yeah. Once, can you open the structure that you created for
Yeah.
sensing?
Yes, sir. Here it is.
Could you show the one that you created at adsorption side?
Adsorption site. This one?
Okay. The periodicity is there in one direction. Okay, sir.
Yes, sir. Right.
Also, you mentioned that you checked on band gap, right?
Yes, sir.
For
Right.
sensing application.
Yes, sir.
Yeah. Could you please show like how did you calculate the band gap for this purpose?
Okay, sure, sir. Sure.
Thank
It
you,
will
sir.
also benefit to number of audience here. See, sir. See, everyone. Here is the structure, that is Armchair graphene nanoribbon, and here with the gas molecule is there. So we are going towards this workflow builder. Now that is not the device, that is the bulk configuration. So here I am just going towards the calculator, that is the only LCO calculator. Now I am going towards the optimized geometry. Why I am going towards the optimized geometry? Because that is not device. We are not optimizing the device. We are optimizing right now only the surface configuration. And now I am opting band structure here. So just type here band structure. From the analysis part, the band structure will get selected, and here you can also go for the total energy measurement. Total energy will able to calculate the adsorption energy. Also, you can calculate the density of states from here. Also, you can calculate the electrostatic difference potential, which we are mostly measuring from this tool. Also, you can calculate the molecule population from here. That is also used for the charge transport analysis. Yeah, I am mostly taking this electronic property. In the LCO calculator, you can see that there are the various parameters which I already told you in the in the device configuration. But I will go for the this K-point sampling. Sir, if you are listening, just see here in the all the three cases it's selected. Now again I will go to backside and I will see here is the structure. So this is my structure. So sir, right now I am going towards this structure because I will tell why I am opting for this right now. So see, C is in the vertical direction, A is here. So one more thing, swap axis is there. So we are swapping from C to A. Now I will go for this work towards the workflow builder. Go towards the set LCO calculator, optimize geometry, and different electronic properties like band structure, density of states, molecule population, and again what to electrostatic difference potential. Okay, right now I'm going towards this. Yeah, again it is coming same, but okay, we'll go towards this. Yeah, here is the K-point sampling. So we can change here, like we can untick this, and in the C axis we will opt towards like 99 or maybe 100 K-point sampling. Why I am ticking this C point? Because our structure is periodic in the C direction and we have already swapped that axis. So in the gas molecule case, yeah, one thing I forget it, we have to change this. In that the density part is there, we have to change this K point to the Monker's peg grid, right, like this, and this is the way we have to select this K-point sampling. This may be the like constant parameter, or you can change with the help of like different literature papers. In the optimized geometry, you see here the various parameters are there. Constraint is there, so we can constrain this x-axis, y-axis, but will not constrain this z-axis because the structure is periodic in C direction. C means Z. Got it? Go toward analyzing the band structure. This is my folder. I'm saving this. Going towards the threaded process with the number of threads for 5. I'm adding this structure. Here is my structure. And now for to start that job, you have to select the start select job and see current task is actually executing the script and status is running and the structure will be stored here. Maybe because of the number of atoms is somewhat there, but it will not take too much time because DFT is widely used for a large number of atoms, so it will not be an issue. But to show you how the band structure will appear, I'm showing you maybe one result in my case. There you will able to understand how this band structure is there. So I'm just checking. Okay, for this structure, I have calculated the band structure. So this is how you will see in the dashboard after that job is run. Then you will see here the band structure will appear. Just you have to click it, and here you will go open with band structure analyzer, and you will click here, and you will see the band structure. So your band structure will appear here. Currently, it is showing the 0 band gap, that is direct band gap, indirect band gap, valence band edge, conduction band edge, that is the LUMO and HOMO level. And you can also export this band structure. Suppose if you are writing some research paper, then you can export this with PNG file, like you can save any name and you can save it. And if you want, see here, it's showing the PNG file, this band structure. And mostly sometimes the research paper is showing that you have to give the data within minimum pages. So what you have to do in this case, go here, grid layout. You can change the dimensions, like suppose row and column is here. Suppose I'm writing here, there. Okay, it changes towards the row. So I'm putting this here. Okay, see how my band structure is get squeezed. So you can use this band structure in your research paper for better comprehension and for better understanding of the reviewers. I hope, sir, I have able to question your query.
Yes, sir. Thank you.
Yeah, thank you so much, sir. Any more question? Again, I am telling my email ID. You can ask me your question. kamalsolanki033@gmail.com. I will try my best. Thank you, Deepak, sir, again for giving me the opportunity.
Yeah, so thank you. So as we come to the close of this insightful session, so I would like to extend my gratitude to both our esteemed speaker for this valuable contribution. So first and foremost, a sincere thank you to Dr. Manoj Kumar Majumdar for sharing this profound research insight on the gas sensing application of the Armchair Graphene Nanoribbons by using this Synopsys QuantumATK softwares. So your presentation provided us with a deep understanding of how atomistic simulation are transferring the landscape of the nanoscale device research. And I would like to thank Mr. Kamal Solanki for the excellent live demonstration. Your practical walkthrough of this quantum 8K platform greatly enhance our comprehension of the tools and also the technique discussed, and also offer a valuable hands-on perspective. So together, you combined expertise has made this session of the faculty interaction webinar series both enriching and the inspiring. So thank you once again, and we will look forward to continue collaboration and learning in this session to come. So
Thank
have
you,
a
Mr.
great evening.
Deepak. Thank you, Mr. Deepak, for the invitation and for giving us the opportunity to present our research. Okay. Hello.
Okay, so yeah,
Thank you.
thank you so much. Thank you
Thank
again.
you. Okay. We are now signing off. Okay.